And so the third method that you need to be familiar with is equating coefficients. And again, you saw this method when we showed a proof of one of the features of Pascal's triangle very early on. And I will go through those identities that were created from the features of Pascal's triangle, again here to demonstrate the method and point out some features and show how the method gets varied, just to develop a broader understanding of this equating coefficients. Now, like with all of them, all questions on show or prove an identity, it's important to take a moment to really identify features of the identity. So, and this to recognise that an identity requires equating coefficients will require that same attention to detail. So if we look at this identity, for example, that we're instructed to show that n plus 1 CR is equal to NCR plus NCR minus 1. Hopefully one thing that might be obvious to you there is that this power, n plus 1, is different to these, and that unfortunately is probably about it. You may look at that and go, oh, but I was thinking that this looks like the sum of coefficients. Will I be able to get this or show this identity simply by a substitution? But like I said, the success of proving and showing identities based on a binomial expansion is very much dependent on you recognizing which one of the methods is appropriate to the question. So the more that you can build the picture of the three different methods and examples that belong to those individual methods, then the better and the bigger picture, more comprehensive that picture is, the more likely you are to be able to identify the method that you will be required to use. As we do look at more examples, then the feature that I've listed below might become a bit more obvious. And it is certainly true in this case that you will only become more confident about which method to use after having looked at lots of these. So although you might go through this and go, yeah, I can understand all of those steps, that doesn't mean that you will recognize the situation where you need to use those steps in future. That familiarity with the process in a particular case will only come through having done lots of questions. So there really is no substitute for doing the practice, building the picture, and paying attention to detail in order for you to be able to successfully answer these questions, because some of the identities, I really must admit, do become quite complex. Okay. I've actually done part of the solution here. So in looking at 1 plus x to the n plus 1, which we would do because we now know if we're going to have n plus 1 CR, then that coefficient must have come from an expansion of 1 plus x to the n plus 1. So, and obviously with a substitution for x. But for now, 1 plus x to the n plus 1 can be split up into 1 plus x times 1 plus x to the n. Expanding that out gives us two binomials to have a look at. So let's look at the left-hand side and get an expression for 1 plus x to the n plus 1, and that will be obviously n plus 1 c naught. I won't put the 1's in, and x to the naught is a 1 plus n. I might just pause this and write the solution. So taking the left-hand side and completing the expansion is pretty straightforward. We are going to include an NCR term, because remember this method is equating the coefficients, and one coefficient, or the general coefficient, would be the coefficient of x to the r, because specifically here in the identity they used NCR, which is implying that we want the coefficients of x to the r. So on the left-hand side, nothing complicated. It's the coefficient of x to the r will be n plus 1 CR. Now, on the right-hand side, which was this, then we're going to take the expansion of the first bit, which is our standard binomial expansion, including the x to the r term going all the way through to NCN. Then the expansion of the second part, which will have an x out the front, and you might notice that I included not the NCR x to the r term this time, because I've got an x out the front. I know I want the term before x to the r, such that when I multiply this, I end up with an x to the r term, and its coefficient is actually NCR minus 1. But we know that in the next line, after I've expanded out the x that was out the front, which came from there, then I will have my x to the r term. So equating the coefficient of x to the r now on the right hand side gives me this expression. I'm not so sure why I didn't leave some space between that and the next example, but never mind. Okay, let's have a look at another example, which I think might be the one that was in the first or second exercise of the chapter. And again, we're showing that the coefficients of Pascal's triangle is symmetrical, and yeah, it's a bit of a variation. We do create two binomial expansions, but they're certainly a little bit along different lines to the nature of the expansions in that previous example, and it really is just, like I've said before, it's exposure to these little differences that you need, and then practice at different examples that use these different little expansions, I guess. Still using the same principle of equating the coefficients, and like we saw previously, yeah, we can match these up with matching up coefficients and then show that you do get that the coefficient of the x to the r term ends up being this pair. So what's the feature of a binomial, identity? What's the feature of an identity that will require you to equate coefficients? I think you're going to see different values of n, or maybe a straight out instruction to use the method